The story so far, what I'm trying to do is I'm simulating a pencil beam of a certain energy. Most of my pencil beam, like I'm not simulating beamlets yet. I'm only simulating one pencil beam, which is beamlet, not plural. In Fred, I am simulating that in Fred, which runs on GPU and which is quite fast. How fast? I'm gonna talk about that and about MCsquare, another Monte Carlo tool which is fast, but not as fast as Fred because it runs on CPU. So what I did was I first ran MCsquare, which is quite similar to Fred in terms of the physics behind it, except how they sample multiple Coulomb scattering. The distribution they take is different. However, they both use the ICRU 63 nuclear model and also the condensed history where they group together the soft collisions, soft Coulombic interactions into one and in one step, and then but they explicitly simulate nuclear events or any hard events where the proton loses a certain amount of energy beyond the threshold. We simulate that explicitly. What I'm trying to say is they have the same algorithm, same model, but they change it here and there slightly. Fred depends on lookup table a lot. It does not uh, try to simulate from scratch. So a lot of thing is in the lookup tables that it uses, and it uses GPU. Whereas MCsquare, multi-core Monte Carlo uh, is more computationally intensive. It does not it it focuses on the physics more than lookup tables, but still it also uses lookup tables as well, but not as much. Anyway, so I ran multi-core Monte Carlo on Hinton, a server or a system with 8 core of CPU and which has 3.6 gigahertz of clock speed, but it also has GPU. And Lawrence, which has 56 threads and 28 cores, but the clock speed is limited to 2 gigahertz. So what I noticed was for 1 million particles and 10 million particles, that is protons, Hinton is faster, quite faster than Lorentz. But when the number of particle increases, when it is 100 million particles, there Lorentz beat Hinton. I I think that Hinton is quite fast for 10 and 100 million uh, because of the clock speed difference. And also Hinton has to first the GPU has to decide how much overhead time, the initialization time it has to take. So for GPU, which is Hinton, Hinton, yeah, it mostly because the initial differences I would attribute to the clock speed. Because yeah, it's I'm making it confusing. Yeah, I'll come back to it later. When I compared both the algorithms, MCsquare and Fred, so you will notice that Fred, its initialization time changes changes a lot with the number of particles. When the number of particles increases, it takes a longer time to initialize the simulation, And what I've noticed in the output log that I have seen it tries to divide the number of particles in groups, like for 10 millions, it divided into groups of 4 million, 4 million, and 2 million. I think while doing those, it takes the initialization time. However, for just doing the simulation, for pure simulation, it's way faster than MC square. And you notice MC square takes almost the same amount of time for initialization. And I got this information from running both of the simulations and taking the output from their log output, taking this data from their log output. What else do I see? Yeah, I see that at least here the magnitude is 10 to the power 4 and here 10 to the power 5, almost 4 times as faster than MC square Fred for 100,000 particles. For 1 million, the speed increases because the GPU speed, and usually it stays somewhere between 8 times. I mean, Fred is 8 times faster than MC square. The wall clock, yeah, the total time which it takes, like it takes it takes time for initialization, and then the maximum time it takes for the tracking, for simulating the particle. That is one of the benchmarking I have done so far. So the system I have access to has two GPUs. So I tried to simulate the particles using two GPU as well as one GPU. And if you can see, only if we compare this part with Fred, here I have used only one GPU. So for example, for 1 million particle, the tracking time Fred takes is 1 second, 1.3 seconds, and tracking time for using two GPUs 1.31 second. Let's see how it goes for higher number of particles. For 10 million, it takes single GPU takes 3 seconds and two GPUs take 2.32 seconds. And with 100 million particles, it is taking one GPU is taking 22 seconds and two GPUs is taking 20 seconds, which is faster than one GPU. And for 1 billion particles, it is 218 seconds tracking time. I'm not talking about the total clock time, which we can compare as well. And it is taking 181. So of course, two GPUs faster than one GPU makes sense, but here lies the silver lining. When I used two GPU, I divided the because you cannot use two GPUs at 100% both of them. I have to divide the maximum uh, work they can do as 50-50. When I do nano dot slash JSRH, uh, something with NVIDIA SMI. So if I don't do that, I get error and I was not able to run it. Or I can do 30-70, but to make it fair, I did it with 50-50, and this is what I got. And I think at the start, for low number of protons, one GPU is faster than two GPUs because two GPU has to synchronize each other with themselves, because at the end they have to give the result. They have to combine the protons, whatever they simulated. Perhaps that could be the cause, but still I have to look into it. Yeah, this is the comparison I was talking about. Yeah, I hope it's clear. So at the starting, one GPU is faster than two GPUs, but later on, the second two GPUs become faster than one GPU, which makes sense because we have two GPUs. but there has to be a detailed and precise answer for that. Maybe I will come up with that in a video, or maybe I'll post it on LinkedIn. Yeah, then what I tried today was I simulated. It's on Fred. It's the both of the simulation is on Fred. So I should have tried on MC square as well. But if you see clearly, you can see that when our particle is monoenergetic, it has a very sharp fall at 155 millimeters. But when the particle is, I mean, the protons, the beam which I'm sending, sorry, the beam which I'm sending is non-mono, like it has with uh, full with half maxima of 5 million MeV. The Bragg peak shifted upwards. It's shallower than the monoenergetic one. Then I thought about the reason why it could be. Then I realized that when we send monoenergetic protons, all the protons have the same energy. That means they will all reach the same depth. That is why this depth is sharper than this one. And why non-monoenergetic particle is not sharper. Um, the reason is that some of the particles, the protons which has low energy, will will deposit their energy before the actual energies. It will deposit energy somewhere here, and this will pull the Bragg peak towards the shallower end. Hence we get a little bit of uh, a diverged peak, not as sharp as this one. Yeah, that is the reason for why the peaks look different. And also, as you can see here, this one is slightly, I mean, we cannot judge it by eyes, of course, but its shape is quite different from this one, because monoenergetic beam are not they are very narrow because they have the same energy, and they go through the material and they deposit all the energy in a very narrow range. But non-monoenergetic particles, they have a range. They don't have the same energy, so they deposit energy not narrowly. So you see this divergence and uh, uh, a blurred, more blurred than the monoenergetic one. This is one of the experiments I tried today. So how do I make the beam spot zero? So in my previous videos I showed you, by putting emittance equal to 0, I was able to make the beam spot completely zero. The pencil beam is with no divergence. I mean, there is no spot. A spot is a part where you usually get the divergence. There is some divergence of the beam. This is the uh, XY slice that you are looking at. I mean, it's coming at you, the proton beam. And this is the Bragg peak, which should not change because Bragg peak is only dependent on the energy of the particle, and of course it's full with half maxima, how much energy is spread in the beam. This I did it for Fred, and I was also trying for MC square whether I will be able to do that for MC square, because they both have different approaches, different philosophy in the code. In Fred, you can explicitly type it, explicitly mention, change the beam shape and size in the code as directly. But in MC square, it's not as quite direct. You have to uh, tweak in the BDL file, the beam directory file, to change the spot size, the divergence. And this is what I got for MC square. And you can see the pencil beam, I almost made it zero, like 0.001. And after a lot of errors and stuff, I got the pencil beam, and of course the Bragg peak would should look similar. So now for same proton energy 150 MeV, for same energy spread 5 MeV, and making the beam spot 0, that is for pencil beam, should should we get the Bragg peak at the same position and of same dose? Well, here I think I may have made some mistake while coding, because in MC square and Fred I checked, I was able to have the same dose, peak dose. I will check again, but in the same case it's 10 to the power minus 12 gray. I'll check again anyway. And so and in fact I did find that they both, for pencil beam case as well, they both align. And also before, I have posted already that with energy spread, same energy spread and same energy, I get the peaks align as well. So yeah, I'm using a lot of so. Anyway, that's the progress so far. A lot of questions and confusions.